Hey, AP Chemisters, this is Mrs. Vandelay bringing you Blankwalle, Chapter 12, Section 6. This is called colligative properties. This is the vapor pressure lowering, the freezing point depression, the boiling point elevation, and the osmotic pressure. So you may be wondering, well, okay, Mrs. Vandelay, what's a colligative property? Well, it's a property that depends on the number of particles dissolved in solution. So what does that mean? Well, we have different kinds of solutes, don't we? Well, the most common solvent, let's use water here. It doesn't have to be water, as we're going to find out a little bit later. All right, but what kind of things can we put in water that makes a solution? It could be gases, although we really don't talk about gases being the solute in this section. It could be liquids. What kind of liquids could we pour in there? Polar liquids. Why? Because nonpolar would not dissolve, would they? So you could put polar liquids, such as maybe ethanol in water or vinegar in water. Or you could have polar solids, let's say like sugars, right? Things like that. Citric acid would dissolve in water as well. And or ionic solids like sodium chloride and calcium chloride, things like that. So by putting these things into water, we are changing the properties of that solution, all right? What kind of properties? Vapor pressure, freezing point, boiling point, and osmotic pressure. We are changing all of those. So for examples, all right, why do some cooks add salt to the water in which they're boiling? Is that to make it nice and salty? Well, maybe, but there could be another reason for putting salt into the water, all right? Why do road crews add salt, which is calcium chloride, to the roads when it's slick out, when it's icy out? All right, well, you probably already know that, all right? It melts the ice. So what does that mean? You are changing the freezing point of the ice, aren't you? It will not, melt at 32. It will melt at a lower temperature. That's why they put it on there. Is there a limit in which that happens? Yes, and maybe they need to put sand on it if it gets too cold, because there's a limit to how far that can melt, all right? So anyway, let's talk about this vapor pressure lowering with a non-volatile solute. What the heck does non-volatile? You might recall earlier that the word volatile means to evaporate. So a non-volatile solute means it doesn't evaporate. And we typically think of those as perhaps solids, all right? So we can put non-volatile solute like a solid. Sodium chloride doesn't dissolve or doesn't evaporate, does it? Okay, so they will actually lower the vapor pressure of a solute. Why? Well, non-volatile molecules do not enter the vapor phase, okay? They do not become a gas, which is going to change the vapor pressure. So now it says fewer molecules are available to enter the vapor phase. So fewer of the water molecules or whatever your solvent is are now going to join that vapor phase. And the answer or the question is, well, why? Well, let's think about what happens here, okay? This is my pure solvent. If I can count, it looks like I have 6 molecules in the vapor phase, and when I put something in it that dissolves, I now only have 4 molecules in the vapor phase. If you look at the little dial up here, the pressure here looks like to be about 3, and the vapor pressure up here looks to be about 2, and that should make sense. That's the ratio of 6 to 4, isn't it? So the question is, well, why, if I put this yellow stuff in here, do I have fewer gas molecules now? Why do I have fewer molecules in the liquid phase evaporating? Well, think about it. What are you putting into the solution? You are putting either something polar or something ionic in the solution. How do I know that? Because if I put in a nonpolar substance, it won't dissolve, will I? You're not going to make a homogeneous mixture. You will not be making a solution if you put a nonpolar something in there. So whatever this yellow stuff is in my picture must be either polar or it must be ionic to put in there. Okay, and what does that do to the green polar solvent? Think about this entire, unit we've been working on. It talks about attraction, right? So what's going to happen here? I wrote polar or ionic solute will increase the attraction, I think I left out the N, within the gas phase. I'm sorry, within the liquid phase. My apologies. So I'll say it again. Polar or ionic solute will increase the attraction within the liquid phase, right? It must be polar to dissolve. Therefore, there must be, some kind of attractions. Those partial positive, partial negatives must be attracted there. So if you have more attraction in the liquid phase, you're going to have fewer of these molecules to evaporate. Okay, so if you have fewer liquid molecules evaporating, that means you have fewer collisions, you have less pressure in the vapor phase. Okay, so that is why it lowers. Now, as you know, there has to be some math involved, all right? And we have something called Raoult's law. Now, Raoult is on your equation sheet. So this is fair game on the AP test, okay? So if you want to, at this point is a good place to pause, look for your equation sheet and look for Raoult's law, all right? So why don't you go ahead and pause this and do that. All right, well, welcome back. Hopefully you found Raoult's law, and it's P of the solution is equal to this Greek letter chi we saw in the last section, which is a mole fraction of the solvent times the pressure of the pure solvent, okay? So this is actually a linear equation of y equals mx plus b. So let's see what's happening here. Let's see here, my y is my pressure of solution. Let's see here, my P of my solvent, all right, or my mole fraction is my X, all right. So what is my, there we go. So what is my M? That's what I'm looking for. Well, what do you think my M is then? Well, my M is the pressure of the solvent. So do you see this line here? The slope of that line is the pressure of that solvent. Now, what happens if the mole fraction is 1? All right, that's a great question. What happens if the mole fraction is 1? What does that tell you? What did we learn about that from the last section? If your mole fraction is 1, then you have a pure solvent, don't you? So if I have a mole fraction of 1, what does that mean? That vapor pressure is the pure vapor pressure, okay? So the solution equals that of the pure solvent. But what if I have a mole fraction of less than 1? It looks like maybe about, I don't know, 0.75 maybe. Well, then I can figure out what the new pressure of the solution, like going back up here again. All right, notice what happened. When I put some solute in there, my vapor pressure goes down, doesn't it? So when I add solute in there, my mole fraction becomes less than 1 and my vapor pressure goes down, okay? So again, what is the slope? Well, the slope is the pressure of your solvent. That is your slope, okay? Let's go to the next page. Okay, so problem 14 says if a solution is said to contain a non-volatile solute, what did that mean again? It doesn't evaporate. Will you write that down? It doesn't evaporate. Why is that so important? Well, it's important because it's not going to enter the gas phase, is it? Okay, so my solute will not evaporate. It will not go into the gas phase, all right? So how does this affect the vapor pressure of the solvent? Look closely at the diagram to help explain, okay? Go ahead and word that yourself, jot something down, pause this, and come back when you're ready. All right, hopefully you've had time to decide what to say here. So what's going on here? What's the first thing I would do? I would start counting. How many gas molecules do you have here? Looks like you have 8. I don't know about you, but I think I can count up to 8. But as soon as you put in the stuff, all right, when you start adding more of this more of the solute, in this case it looks pink, what happened to the number of particles? I go from 8 down to 5. So what happened? My mole fraction went down. It's no longer a pure substance, all right? So my mole fraction goes down, as does my vapor pressure, okay? I have fewer gas molecules in solution. Why? Because when you add a non-volatile solute, you're going to increase the attractions within the liquid phase. Therefore, you're going to have fewer molecules evaporating. Therefore, you're going to have less pressure, okay? Oh, that's kind of like a wordy thing. Yeah, I know, but it's kind of like your polarizability thing too, all right? All right, let's go to problem number 15. Oh, it looks like a math problem to me. Calculate the vapor pressure at 25 degrees if a solution contains 99.5 grams of sucrose, which is C12H22O11, and 300 mils of water. The vapor pressure of pure water at 25 is 23.8 torr. Assume the density of water to be 1. All right, so let me scroll up and set this problem up. All right, so what's going on here? Well, let me do something real quick. Okay, so what's happening here? Well, I need to find the vapor pressure of this solution. So I know I need the P of solution is the pressure of the pure solvent times the mole fraction. Okay, well, I need a mole fraction, don't I? So I need this. Notice it's the solvent. Don't be lazy. Make sure you write this word solvent down. Why is that important? Because what's your numerator here? You put solvent on the top, and then it's over the total number of moles of solute and solvent. Hey, that's why we learned that in section 12.5. So now what do I need to do? I need to start calculating moles of the solvent and the solute. Hey, what's my my solvent? I think it's water, isn't it? All right, so I have 300 grams of water, and I know it's 18.02 grams per mole. So if you do your calculations, hey, what do you get? I get 16.6. Okay, now what? I need to find moles of my solute. All right, so I have some sucrose. And when I do that, the molar mass, I'll put it down over here, is 342.34. And when I do that, I get 0.291 moles. So I think I'm ready to find my chi. How about you? So I put my moles of my solvent, which is 16.6, over 16.6 plus 0.291. And if you do your math, what do you get? Nope. Well, I'm really sorry about that. I hit the wrong button, didn't I? All right, I get 0.983. So that's my chi. So look what I'm doing right here. All right, here is my my vapor pressure is my y-axis. Here's my x-axis. That's my mole fraction. So if I had pure solvent, all right, so if my 1 goes up here, I get 23.8. So if y equals mx plus b, y equals 1 times 23.8, that's my slope, and that's equal to 23.8. But my mole fraction is right here. So what kind of value would I expect to get? Well, go click, 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 click up here. All right, and then I'm going to go over here, and it's going to be less than 23.8, isn't it? Well, what is my actual value going to be then? All right, well, it's going to be 23.8 torr times the mole fraction, that's my x, there is no b, and what do I get? I get 23.4. So what's my value right here? This is going to be 23.4. What is this going to be? Hang on, torr. It's going to be 23.4 torr right there, okay? So that's how you do this problem. So let's see. Let's go on to problem number 16, okay? Why don't we pause this and you do this all by yourself, all right? And then when you're done, come back and see what you get. Okay, if you read this, you see it's a very similar problem, but what was really nice, you're solving for the mole fraction. This is a whole lot easier now, isn't it? They gave you the pressure of the solution. They gave you the pure vapor pressure of the, I guess, of the water, and you're asked to solve for the mole fraction. So when I did this, all right, I'll divide by sides, both sides by 9.21. I got 0.856, and that's your chi of your what? Your solvent, which is what? Your water, okay? Then what? Well, what is the mole fraction of ethylene glycol? Well, how did I get this number without doing anything? What do you notice they both add up to? 1 All right, is that true? Yes, your mole fractions, when you add them up, will always add up to 1. Okay, so that makes your life quite a bit easier, and we're going to see how useful that is very shortly, all right? But my 15 minutes are up, so don't wait to be great, and we're going to see you shortly in part 2. Bye-bye.